Okay, so to wrap up Chapter 7, we're going to be looking at sample means. Sample means are going to behave very similar to sample proportions. Again, notation is going to be really important, like it was with those. Okay? And again, behavior is going to be very similar. So when we're looking at the mean, and the mean of the sample, right, so our x bar here, when we take the mean of a simple random sample, from a large population, then the mean of that sampling distribution should be equal to the population mean. Same as we had before. This mean is again an example of an unbiased estimator. So my mean of my sampling distribution, my sample means, should be the same as the population mean. My standard deviation for the sampling distribution of the mean, so again, remember we're talking about a sampling distribution here. So we're talking about a dot plot, and every single one of those dots represents a sample that we took. So the standard deviation of the sampling distribution of the mean is this formula here, which is our standard deviation divided by the square root of the sample size. Remember, lowercase n is our sample size. Same as with proportions as well. We've got to make sure those 10% conditions are satisfied to be able to use that standard deviation formula. And so again, when you work these problems, you have to show that you know this condition is satisfied. You have to show your work for it, and you have to state or somehow show that you know what it means. That you know that my population is 10 times larger than my sample, or that your sample is less than 10% of your population. Okay, so let's look at some examples with this. Okay, so our example here is dealing with wines. So sulfur compounds such as dimethyl sulfide, DMS, are sometimes present in wine. DMS causes off odors in wine, so winemakers want to know the odor threshold, the lowest concentration of DMS that the human nose can detect. Extensive studies have found that the DMS odor threshold of adults follows a distribution with a mean of 25 micrograms per liter and standard deviation of 7 micrograms per liter. Suppose we take an SRS of 10 adults and determine the mean odor threshold for the individuals in the sample. What is the mean of the sampling distribution of X bar? And explain. Okay, well, this is the same as we saw with proportions again. Okay, my mean of my sampling distribution is equal to the mean of my population, which in this case they told us was 25 micrograms per liter. And by using the proper notation here, so by using my proper notation here, this becomes my explanation, as to how I knew this. So for part B, what is the standard deviation of the sampling distribution? Check that the 10% conditions are met. As a general rule, you are not going to be told to check that the 10% conditions are met. That's something you're going to need to know to do to get full credit. Okay, so on part B, if I'm going to check my 10% conditions, because I should do that first, you're really not going to be given any problems on your AP test that don't meet those 10% conditions, but the expectation is that you're still proving that they do. Okay, so if we're checking them, we had a sample size of 10 adults, so 10 times 10 equals 100 adults, which is definitely less than 10% of my population of adults. Okay, so when you explain your 10% condition, just this right here is not going to be enough. You need to make sure that you state what that 100 means, okay? That you tell them that you understand what the condition what the condition is that needs to be met. The fact that 100 needs to be less than 10% of my population of adults. We like context, right? So now when we actually calculate our standard deviation, since we can use the formula because our 10% condition was met, we're going to have our standard deviation of the population, which is 7, over the square root of my sample size, which is 10, which gives me 2.214. So that gives me my standard deviation of the sampling distribution of X bar. So when dealing with these sampling distributions here, the sampling distribution of the mean is going to have the same shape as the population. So if the population is normally distributed, then the sampling distribution of the mean is also going to have a normal distribution, which will allow us to solve problems using those normal properties that we already know how to work with. Let's look at this one regarding young women and their heights. Find probabilities involving the sample mean. So the problem is we have the height of young women follows a normal distribution with a mean of 64.5 inches and a standard deviation of 2.5 inches. We're asked to find the probability that a randomly selected young woman is taller than 66.5 inches and show our work. We're also asked to find the probability that the mean height of an SRS of 10 young women exceeds 66.5 inches. So part A is a typical normal problem that we're used to. Okay, so when we're doing this, we need to be showing our work, drawing our pictures, right? So I've got my normal curve here. I need to make sure I go ahead and label this 64.5 inches and a standard deviation of 2.5. So that 64.5 would be here. And what I'm looking for is the probability that one individual young woman has a height greater than 66.5. Okay, so I'm looking on my curve. Let's see. 2, so she's not quite one standard deviation away. So I'm looking for this right here. So this helps in showing my work. Well, one, it helps me make sure that I know what direction I need to go, especially if you're using a table as opposed to your calculator. Or if you're using your calculator, it helps you know what your upper and lower boundaries are and such. Okay? But it also helps and really makes a difference in the showing your work credit portion. Okay? So I can calculate z-scores for this. Okay? So I can go ahead and I can calculate her z-score, which is going to be her actual height, that's 66.5, minus the mean over the standard deviation of 2.5, which gives her a z-score of 0.80. So I can either then go use Table A and find the probability of somebody. I can then use Table A and find the probability that they have a z-score greater than 0.8, which is equal to whatever Table A shows me. Okay, and since this one is a greater than situation, it would be 1 minus whatever Table A shows me. Or I can use my calculator. Right? I can use my normal CDF function. I can identify everything that I'm working with. So in this case, my lower would be 66.5. My upper would be some big giant number. My mean would be 64.5, and my standard deviation would be 2.5. And when I plug that all into my calculator, I get 0.2119. Okay, so now I have my value, and now I need to actually answer the question. I need to state what that means. Okay, and so what that means is the probability of choosing a young woman at random that is going to have a height greater than 66.5 inches is about 0.21, or 21% of the time. Okay, part B here is asking about the probability of an SRS, the mean height of an SRS of 10 young women exceeding 66.5 inches here. Okay, so if I'm looking for the probability that the mean height of an SRS. Okay, so I'm looking at the probability that my X bar is going to be greater than 66.5. So I'm basing this off of a sampling distribution of mean heights from a bunch of samples of 10 young women, and we measured their height and took their mean, the mean height. So the mean of the sampling distribution here, right, is going to be equal to the mean of the population, so that's going to be equal to 64.5. Okay. My standard deviation, however, is not going to just be equal to it. I need to make sure my 10% rule is met, my 10% conditions are met. So I had 10 times 10 gives me 100. So I know that there are way more than 100 young women out there. Okay, so my sample is definitely less than 10% of my population. So I can use my standard deviation formula. So my standard deviation of my population was 2.5. My sample size was 10, so over the square root of 10 gives me 0.79 for my standard deviation. Okay, because my population distribution was normal, then that means that my sampling distribution is going to follow that same shape. Okay, I have the same mean of 64.5, but I have a very different, and I label my curve here, right, 64.5, but this time I have a standard deviation of 0.79. So my standard deviation is definitely different. Okay, I want to know that the mean, the likelihood of a sample of 10 women has a mean of 66.5 or higher. Well, this time that 66.5 is going to be like way over here. Okay, because my standard deviation is much smaller this time. So I can show my work again. I'm showing my work again. I can do a z-score situation again. This time, though, my z-score is going to be divided by 0.79 instead of the 2.5 that it was before. So the 66.5 minus 64.5 over the 0.79, which gives me this time a z-score of 2.53. So I can find the probability that they have a z-score greater than 2.53. So remember, that's going to be 1 minus whatever it is that you find in your table. Okay? Or I can use my technology, my normal CDF. I can label everything out. My lower is 66.5, and this time I put in a standard deviation of 0.79. Okay? Either way, I'm going to get an approximate area of about 0.0057. So this is really, really unlikely. Okay? There is a less than 1% chance that we would get an SRS of 10 young women whose average height is greater than 66.5, meaning that sample, maybe it wasn't random. Maybe you pulled the entire University of Texas women's volleyball team, and that's where your sample came from, and it wasn't a very good random sample. Okay? But this is what we've been talking about with that 5%. This is less than 5%. Okay, so this is very, very rare that this would happen by chance. You would be surprised if this did happen. Okay, so let's look at the central limit theory. What if your population is not normal? Okay, what are you going to do about that, and how are you going to calculate things? So with the central limit theorem, basically what that states is that even if my population isn't normal, okay, as my sample gets larger, okay, and if my sample is large enough, then my sampling distribution of the sample mean is approximately normal. Okay, so again, taking an SRS from any population, okay, any population with a mean and a finite standard deviation, then my central limit theorem, or my CLT, states that if my sample is large enough, then my sampling distribution of the sample mean is approximately normal. If we look at the graphs that we have up above, A, B, C, and D, okay, the original population graph basically looks kind of like this, like with a peak, and then another kind of weird peak, and then a big peak over here at the end. Okay, so definitely not a normal situation here. Okay, and so if we look at these sampling distributions that we have here in A, we've got the distribution of the means with a sample size of just 2. Okay, in B, I've got a distribution of the means with a sample size of 5. In C, there's got a sample size of 10. And in D, I have a sample size of 25. I can see as my sample size is increasing, okay, my sampling distribution of the mean is becoming more normal. Okay, and so kind of our given number is that your sample size needs to be greater than or equal to 30. Okay, that as a general rule is a big enough sample size where your sampling distribution will start to become more normal. So we'll look at an example with this, and then we will be all set with Chapter 7. Okay, so what we have going on here is an example here with air conditioners. Your company has a contract to perform preventative maintenance on thousands of air conditioning units in a large city. Based on service records from the past year, the time and hours that a technician requires to complete the work follows a strongly right-skewed distribution, with a mean of 1 and a standard deviation with a mean of 1 hour and a standard deviation of 1 hour. In the coming week, your company will service an SRS of 70 air conditioning units in the city. You plan to budget an average of 1.1 hours per unit for a technician to complete the work. Will this be enough? So let's kind of figure out what our problem is. What are you looking for with this? What you're looking for here, I'm looking here to determine if the probability of my average maintenance time, so that's what my X bar is, right? This is my average maintenance time. I want to see if that X bar for 70 units is greater than 1.1, right? If my average time here is greater than 1.1, okay, and if you want, you can go ahead and make note in there that you've got for 70, you're servicing 70 units. Okay, so let's look at my distribution. Okay, so it told me that this distribution is right skewed. Okay, it gave me a mean of 1 hour, right? So my mean of my sampling distribution is equal to the mean of my population. So that is going to be 1 hour. Okay, I need to check my standard deviation. Can I use my formula for standard deviation? Are my 10% conditions being met? So I'm servicing 70 air conditioners, which is equal to 700. Basically, I need a population of 700 or more air conditioners in the population. It says that your company does maintenance on thousands of air conditioners. So we meet that 10% condition. My sample is less than 10% of my population. So I can use my standard deviation formula. So my standard deviation here of the sample is going to equal to my standard deviation of 1 over the square root of my sample of 70, which gives me a standard deviation of 0.12. Okay, and then now, though, it says that I'm strongly right skewed. However, I have n is equal to 70, which is greater than or equal to 30. So my normal or large samples condition is being met. This again is that central limit theorem that we just talked about, but this terminology here, this normal to large sample conditions, is one you will also see, so we're going to start using it some too. What you cannot do is what I just did. Okay, you cannot write this down like this. Okay, you cannot write this, name the condition, and give them a check mark that says it's done. Like always, you have to put it in words, but like always, that becomes a big giant mess on the iPad. Okay, so keep that in mind. You've got to put that in words. You know, my sample size of 70 air conditioners is greater than 30, therefore the normal to large sample conditions are met. Okay? Again, always putting your symbols, your information into words. So now that these normal conditions have been met, then I can draw my curve. That's a terrible starter curve. It's a normal curve. I can assume it's normal with a mean of 1 and a standard deviation of 0.12. So I'm right here at 1. Okay, and I wanted to know if my probability of a sample of 70 air conditioners is going to be greater than 1.1. So about here, I want to know this probability right here. Okay, and I can calculate my z-score. I can use my calculator. Hopefully by now you know how to do both of those things. If you do not, you need to be figuring out when you are coming into tutoring to get that figured out. Okay, from either one of those things, you should get about 0.2023-ish. Okay, it could be a 0.203 if you're using the table. So it just kind of depends on where it comes from. And then the last thing that you need to do now is you need to actually answer the question. You need to write down the answer to the question. Okay, so in this particular case, if I'm budgeting 1.1 hours per unit, I've got a 20% chance that they won't complete the work in the time allotted. Okay, I've got a 20% chance that it's going to take longer than the time that would be allotted to service those 70 air conditioners. Okay, and so then if they were asking you some kind of follow-up as to whether the business should do this or not, you'd have to make the judgment call as to whether that 20% would be, if that's too much risk, that you might have too many super mad clients. If it's an okay risk that you could kind of work around it, but you could use that number in the business setting to kind of determine whether this is enough time or not. Okay, and so that wraps up chapter 7.